We're picking up where we left off. We were talking about temperature and the temperature scales, looking at Celsius, Kelvin, and Fahrenheit. The Celsius scale is based on the freezing point and boiling point of water being 0 and 100 degrees. What's different between the Celsius and Fahrenheit scales is not only the size of the degree, but also the 0 point. On the Fahrenheit scale, water freezes at 32 degrees, and that's 0 on the Celsius scale. So when we convert between Fahrenheit and Celsius, we actually need to use an equation. The Kelvin and Celsius degree are the same size. The 0 is offset, and so the equation for that conversion is much simpler. Kelvin is the Celsius temperature plus 273.15. We'll do a couple of examples. Gallium is a solid metal at room temperature, but will melt to a liquid in your hand. Unfortunately, I believe it's toxic, and so we can't play with it. The melting point of gallium is 85.6 degrees Fahrenheit. What is this temperature on the Celsius scale and on the Kelvin scale? So this is a word problem, right? There's a whole bunch of words in here. It doesn't just say convert 85.6 Fahrenheit to Celsius. The words make things confusing for a lot of students. There's two kinds of people in the world, I've noticed. People who like story problems or word problems, and people who hate them. And I don't run into very many people who are kind of wishy-washy on word problems. People either get it or they don't. I'm here to help those of you who don't get word problems. What you want to do is always read all the words, read through the problem so you kind of have an overall picture. Then go back and look for the numbers. The numbers are going to be important. So we only have one number in this problem. Well, let's write it down. 85.6, always write the unit. Units are your friends. They'll help you figure out what you're supposed to do. So that's the only number we're given. What is the question? What are they trying to get us to find?
Convert Kelvin.
Yeah, they want what is the temperature Celsius scale. So we need to convert degrees Fahrenheit to degrees Celsius. Temperature conversions use equations. So what we need is the temperature conversion. And this is one that you need to memorize. So there it is right there. So we write down the equation. Then we look to see if we need to rearrange it or not. We're trying to find degrees Celsius. This says degrees Celsius equals, so we're good. We don't have to rearrange. We're going to take this Fahrenheit temperature and plug it in where the F is. So this is going to be 85.6 minus 32 divided by 1.8. When you do this on your calculator, make sure that you finish the subtraction before you divide or you'll get the wrong answer. If you have your calculator with you, get it out and make sure that you're speaking to it correctly. My calculator is giving me 29.777, a whole bunch of sevens. I don't even know how many, and then an 8 at the end. And the unit on that would be degrees Celsius. Anybody else get that? When you're doing a calculation, it's very easy to punch a button wrong, right? Do a calculation twice. If you get the same answer both times, you probably did it correctly. If you get two different answers, do it again and go for best 2 out of 3. That way you can avoid just dumb button pushing mistakes. Now, that's an awful lot of digits. We're going to talk about significant figures, but we don't really need to know those to do temperatures. Basically, what you want to do with a temperature is you want to look and see what decimal place does your starting temperature end in. This is the first decimal place, the tenths place, and so then we're going to round this off to the tenths place as well. So we're gonna stop this here, and we're going to say that's 29.8 degrees Celsius. Any questions? Should be pretty straightforward. That's not all, though. This one is asking us two things. What is that in Celsius and what is it in Kelvin? Well, we're going to need an equation, so we can go back to that previous slide. The equation to convert from Celsius to Kelvin is Kelvin equals the Celsius temperature plus 273.15. We want the Kelvin temperature. This equation uses the Celsius temperature, and we just calculated that. So we're going to use the answer we just found in this equation. We're not going to use the temperature in Fahrenheit because that wouldn't work. So we're just going to put that number in there, 29.8 plus 273.15. And a calculator. It's giving me that. Anybody else get that? Thank you. So the unit on that is just capital K. It's not a degree Kelvin, it's just a Kelvin. If we're looking at number of decimal places, we're going to go to this starting number or even this starting number and say, okay, this was known to the first decimal place. We should round this answer to the first decimal place. And so the best answer is 302.9 Kelvin.
Shouldn't that be 0.95? Yeah.
Okay, yes. I was using the, never. I did that on purpose.
Testing.
I was testing you. No, I wasn't. I just make mistakes. 9.5, okay. So that changes the final answer a little bit, doesn't it? Because if we're going to keep that 9, when we round, and we'll go over this again, when we round, we look at the next digit. If it's 5 or greater, we round up. So the 5 makes us round the 9 up to a 10, and then the 2 gets rounded up to a 3. So we're going to end up with 303, and then we still need that decimal place. It's 0.0 Kelvin. Okay, did I do it right that time?
When you add the Celsius, when you plug in the Celsius into the Kelvin equation,
Mm-hmm.
do you use what you rounded up to, or do you use what you had in your calculator before?
Well,
I had in my calculator before, and I got the answer you got before.
that's a good question. We should use the unrounded number, and that's how I ended up with that number. Is I used this one, and that's a very good point. And we'll talk about that when we talk about significant figures. When you're going through and doing multiple calculations, it's best not to round things off. And so I accidentally did it the correct way, and now I've fixed it to the incorrect way. Is that going to be a deal breaker? No, because the other answer I ended up with was 302.9. Is that really close to 303.0? Yes, it is. We're going to talk about something called uncertainty, and when we record a measurement, there's always uncertainty in the last digit. And so when we record 303.0 or 302.9, we say it's like plus or minus 0.1. And so there's a little bit of uncertainty. So like mastering chemistry is probably where you'll run into the most picky about stuff like that. And he will probably take both of those as correct. But thank you for bringing that up because I don't know, had a brain fart. Any other questions? Prefix multipliers in the metric system. I am going to assume that you are proficient in scientific notation. If you are not, you should see Appendix 1A for a review of that and ask me lots of questions outside of lecture, and I'll help you bring you up to speed. But we don't have time to go over scientific notation. The prefixes used in the metric system are multiples of 10. So they're 10 to the third, 10 to the minus 6, these sorts of things. And so they tie in very nicely with scientific notation. The multipliers change the value of the unit, just like the exponent does in scientific notation. So if we look at the unit kilometer, the prefix kilo means 1,000 or 10 to the third. So 1 kilometer, kilo multiplies meter by 1,000. So a kilometer or a kilometer is 1,000 meters or 10 to the 3 meters. And the metric system is something that you should also have seen before, but that doesn't necessarily mean that you remember it or that it made sense at the time. We can do this with any of the metric system prefixes, and they can be used with any of the units. And the nice thing about this is you memorize that one set of prefixes, and you can do all the conversions you want to in the metric system. It really is much easier than the English system. Does anybody know how many tablespoons are in a cup? How many?
I think there's 4 per quarter cup.
That sounds like it might be right.
16.
But I would not, you don't sound super confident. I always have to look that one up. There's all these weird relationships in the English system. In the metric system, it's all factors of 10, and they all use the same prefixes. So let's say we were doing 1 microgram. Well, micro is an abbreviation for 10 to the minus 6, kind of like a nickname for 10 to the minus 6. So this is 1 microgram. We can write that as 10 to the minus 6 grams. Instead of this symbol micro, I'm just going to write what it means. And so these two things are equal. And that's how you make a conversion factor in the metric system. On one side of the equal sign, you write the prefix. On the other side, you write 10 to the whatever that it means. Now, this number might be challenging to put into your calculator, but if we multiply it by a 1, that doesn't change its value, but now it looks like scientific notation, and we can do that on our calculators just fine. These are the prefixes. I think there's a couple more on here than is on your memorization quiz material, but you need to memorize these. The most important ones in chemistry are going to be kilo, deci, centi, milli. Those are the ones we use a lot. They give you, in standard notation, the multipliers. I can't look at this one and tell you how many zeros are there. I have to get my finger out and count them, and that makes me feel like I'm in kindergarten. I think it's much better to memorize the powers of 10, because then you don't miscount zeros. Most of these powers are multiples of 3. So here we've got 3, 6, 9, 12, 15. There's a couple here in the middle that are not powers of 3 or multiples of 3, but the rest of them are all multiples of 3. So you just need to memorize those. So let's do a little bit with those. How long is 4.5 megameters in meters? We first have to ask ourselves, what does mega mean? Capital M is what?
10 to the 6.
10 to the 6. So, you know, when they say the movie star is, oh, he's making mega bucks. Millions of dollars. Mega literally means million. So capital M is 10 to the 6. So 4.5 megameters is equal to 4.5 times 10 to the 6 meters. So you can just interchange the prefix and its meaning 10 to the whatever. If we had a number like this, 7.13 times 10 to the minus 9 liters, asking us, well, what would that be in nanoliters? Nano is lowercase n, and that means 10 to the minus 9. Nano and 9 are similar in sound, right? So that can help you remember. Well, this part of the number, that is equal to the n. N stands in for 10 to the minus 9. So 7.13 times 10 to the minus 9 liters is the same as 7.13 nanoliters. It's convenient to have a unit that is close to the size of the quantity that you're measuring. If you're measuring very, very tiny volumes, it's nicer to use nanoliter than liter. Just like if I was going to measure the length of my calculator, I wouldn't want to use miles or light years or something silly like that, right? Because the number would end up being ridiculously small. But if I'm measuring the distance between Fresno and San Francisco, I don't want to measure that in inches because that number is going to be too large. So it's convenient to have units of different sizes. The metric system uses prefixes to change the size of the units to make them convenient. Any questions? We've been talking about the basic units, units of length and time and mass. Now we're going to talk about derived units. These involve combinations of other units. A rate of speed is also a derived unit that can be measured in miles per hour. You know, you're going 70 miles per hour on Highway 99, or it could be measured in meters per second, but it's two of those other units combined. Volume is a measure of space. We can measure space by let's draw a cube. So here we have a cube. And this gets a little bit into geometry. How would we measure that cube and calculate its volume? Yeah, base times height times width, or length times width times height. You know, it doesn't really matter exactly how you say it. But you need to measure the three different dimensions. Let's call this length, and that one's height, and this one's width. You'd measure each side of the cube, and then you multiply them. Well, let's say that this is 1 foot on each side. So each of these, this is 1 foot. Well, what does the volume end up being then? We've got 1 foot times 1 foot times 1 foot. 1 times 1 times 1 is still 1. What is feet times feet times feet? Feet cubed. So we've taken a unit of length, the foot, and made it into a unit of volume because it's cubed. Any unit of length when cubed becomes a unit of volume. Same is true for meters, millimeters, and centimeters. When we cube them, it becomes a unit of volume. Just like in the English system where we would measure volume of liquid, you know, you don't measure gallons in cubic inches, right? You measure it, what did I say? You don't measure gallons in cubic inches. You don't measure milk in cubic inches. You measure it in gallons. In chemistry, we don't generally measure liquids in cubic centimeters or cubic millimeters. We'll measure it in liters and milliliters. Here's a big cube. It is 10 cubes on each side, 10 cubes across, 10 cubes up, 10 cubes back. So how many cubes are in there? 1,000. 10 times 10 times 10. 1,000 cubes. So if there's, so that's, I don't know what I'm doing today. Each of those cubes is 1 centimeter. there's 10, I don't even know where I'm going. I just like completely lost my train of thought. Just jumped the tracks. So there's 10 cubes here, and they're each 1 centimeter, so that's 10 centimeters. That's what I was trying to do. So 10 centimeters on one side, 10 centimeters on the other side, and 10 centimeters on the third side, and that comes out to be 1,000 cubic centimeters. Or we could write it as 10 to the third cubic centimeters. What's the prefix? Let's not go there just yet. What is the volume of the little cube? It's 1. It's 1 centimeter on each side, so the volume of this guy is 1 cubic centimeter. That's that guy. So this big one is 1,000 cubic centimeters. It's 1,000 of those little guys. This volume is also called a milliliter. A cubic centimeter and a milliliter are exactly the same size. They're just different names for the same unit. In medicine, they call a cubic centimeter a cc. You know, you hear on the doctor shows, give him 5 cc's of this stat, right? Cubic centimeters. Scientists say milliliter. It's the same unit. So this is a milliliter. That means that in this big block, there are 1,000 or 10 to the third of those milliliters. What does the prefix milli mean? 10 to the negative 3. So this is 10 to the third times 10 to the negative third liters. What's 10 to the third times 10 to the minus third? Uno. 1. 1 liter. 1 liter is 1,000 milliliters. Or we can say 1 milliliter equals 10 to the minus third liters. That did not go well. You might want to watch Wednesday's video on the other YouTube playlist. That's bad. These are some common units and their equivalents. Different conversion factors for length, for mass, and for volume. I am going to expect that you memorize the metric prefixes and can do any metric conversions without being given conversion factors. There's one on here that is not a metric factor that I do want you to memorize, and that's this one. The relationship between inches and centimeters. 1 inch is exactly 2.54 centimeters. We end up using that one quite a bit, and you need to memorize it. The rest of them, well, this one's all metric, but the rest of them that aren't metric, if you need that on an exam or something, I'll give it to you. You don't have to go and memorize all those things. Another important thing is to remember is that 1 cubic centimeter is the same as 1 milliliter. That's a little factor. It's a simple thing, but you overlook that, and it can make some of those problems really difficult.
Is that true for all liquids? So we say 1 centimeter cubed is equal to 1 centimeter?
Well, 1 cubic centimeter is a unit of volume, and milliliter is a unit of volume. So the density is not the same, but the volume is the same. Any other questions? Density is another derived unit. It's the ratio of mass to volume. We can write an equation for that. Density equals mass over volume, or D equals M over V. Common units for liquids and solids. For liquids, grams per milliliter. For solids, gram per cubic centimeter. And over here we have a table just giving some densities of common substances. You don't need to memorize this table except for this one. At 4 degrees Celsius, the density of water is 1. 1 gram per cubic centimeter, or 1 gram per milliliter, because they're exactly the same thing. You should know that. This statement here is going to come up on the worksheet this afternoon. Density is a physical property that depends on temperature. The mass of something doesn't change with temperature, but the volume of a substance can change with temperature. The amount of that change varies from substance to substance, but the volume does change at least a little bit with temperature, and so density does depend on temperature. That brings us to intensive and extensive properties. Intensive properties do not depend on the size of the object or the amount of substance. These are things like the density, the melting point, the color. If you have a piece of wood and you cut it in half, does the color of the wood change? No, it's still wood. The length of the log is different. The weight of the log is different because you cut half of it off. The color's the same. The density is the same. Density and color are intensive properties. The length and the mass are extensive properties. They depend on how big the object is, how much of it you have. Water freezes at 0 degrees Celsius. Ice melts at 0 degrees Celsius. If you have one ice cube, it will melt at 0 degrees. If you have 5 ice cubes, they will melt at 0 degrees. If you have a room full of ice cubes, they will melt at 0 degrees Celsius. It doesn't depend on how much. That's an intensive property. I kind of remember this by thinking intensive and intrinsic. So an intensive property is intrinsic to that substance. Doesn't matter if there's more or less substance. It always does that. Intensive properties can be used to identify a substance. So you can measure the density of something and identify what kind of a metal it is. You can look at 2 pieces of metal and have at least a clue about which substance they are by their color. If you look at a nickel versus a penny, the penny is made out of copper, and you can tell that it's copper because of its color. If you have a bigger chunk of copper, like on a roof, it's the same color until it corrodes from the water. So extensive properties depend on the amount. Here's another word problem. This one has a lot of words. We always called them story problems when I was in school, and I think that sounds more friendly, doesn't it? Oh, it's a story problem. This one actually has a little bit of a story. A man receives a platinum ring from his fiancée. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? So we read the question. Now we're going to go back and find the numbers, write them down, identify what they are. So there's 2 numbers in here, 3.15 grams. The unit is really, really important. And we've got 0.233 cubic centimeters. We need to identify what these are measuring. The units help us. Here it says mass of, so that's a huge clue that this is the mass. But the unit gram is also a clue because gram is a unit of mass. So this is the mass of the ring. And he finds that it displaces 0.233 cubic centimeters of water. That might not mean much to you right now because we haven't talked about measuring things by displacement. But cubic centimeters should mean something. What does a cubic centimeter measure? Volume. So this must be the volume of the ring. The units tell us that. We were just talking about intensive properties and how they can be used to identify a substance. Density is an intensive property. Here we have the mass and the volume. Could we calculate the density of the ring? Yeah, we could. So we should do that. So we calculate density with the equation. Density is mass over volume. So we're going to take the mass, 3.15 grams, and we're going to divide by the volume. Always, always, always write the units. So now we get out our calculators and we go 3.15 divided by 0.233 equals, and we write down what it says, 13.519333. We look at the units, grams and cubic centimeters. Units are like variables in algebra, x's and y's. We look at that and we're like, yeah, there's nothing's canceling out or simplifying, so let's just write them down how they are. Grams over cubic centimeters.
Is that 15.?
Yes, I'm having troubles with my decimal points. Thank you. We're going to talk in just a few minutes about what to do with all these extra digits. We're not going to worry about it right now. There, we calculated the density of the ring. Did we solve the problem? No, because the question is the ring platinum? We need to look at the chart. So we'll go back here. Platinum has a density of 21.4 grams per cubic centimeter. Is this platinum? No. No, it's not. It appears to be mercury. Could a ring be made out of mercury? Nope. Yeah, not unless you're like, in a really cold place. Because it's like making a ring out of water, right? Mercury's a liquid at room temperature, so this is not going to work. I should probably revamp that question because that's a little bit silly. But the density is not the same, and so the answer is no. It is not platinum. It's something else. How could it be the density of mercury without being mercury? Combination of two different substances. Perhaps it's platinum mixed with something else like aluminum that's lighter. And so it could have the appearance of platinum, but the density will be off. The wedding's off. Well, actually, there's another problem. Same story. The woman in this example is shocked that the ring is fake and returns it. She was not trying to cheat her fiancé. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? Well, we just did one like this, and so this is going to be easier, right? We know, we need to find the density of it, and this is our mass, and this one, it even says volume, 4.53 grams divided by 0.212 cubic centimeters. And we do the math. And this one comes out to 21.3679245.3. And so we can say yes. This one is platinum, because the density of platinum is 21 point something. This stuff I'm writing here, that's what's called showing your work. Okay? I don't want to see you doing long division or adding things out and carrying ones and stuff. I expect that you're going to do the actual calculation on your calculator. What I want to see as work, and you should write down your work for everything, is if there's an equation, write that down, and then put the numbers in with their units, and then show me the answer. Because if you make a mistake, we can look at your work and figure out where you went wrong without just starting over. And showing your work is really important as a scientist, because when you, in your notebook, you're collecting your data and you're coming up with results, those results, someone else needs to be able to look at them and make some sense out of them and figure out, how did you get to those numbers? Did you wave a magic wand and poof, the numbers became what you wanted? No, there has to be some work shown so we can tell what you did.